Hey folks, welcome back to the Combo Class bonus channel. I still am recovering from COVID, although I'm starting to get better, but I wanted to show you some cool mathematical stuff anyway, so I figured I'd film a little mathematical lecture myself to teach you some awesome patterns of how many squares are in this shape, how many rectangles are in this shape, how many of different sorts of triangles are in that shape, and how these relate to other patterns with numbers and even with three-dimensional shapes. So let's define this as a square grid shape with a width or size of 4, because that's how far across it has. And this one will be a triangular type grid with, once again, 4 on each very edge. Not counting all the triangles we could pack into there. We'll get into that in a minute. But we'll call that a size 4 triangle and that a size 4 square. And to analyze these bigger ones, we're going to want to look at some smaller examples and start with the simplest question of how many squares are in a smaller version of this square guy. So, looking at the 1, 2, and 3 sized squares, let's first break down the components of what types of square could they contain. Now, this one could only contain one of its own size. This could contain the smaller size or one that's the size of a 2 by 2. This one could contain the smallest, that 2 by 2, or a big old 3 by 3 of size. Now, how many of each of these components fit in there? Well, the biggest size, there's just going to be one for each one, because we can fit one of the minis, one 2 by 2 all the way around that, and one 3 by 3 all the way around that. So how many of the smallest? Well, there we have 1, there we have 2 times 2 is 4, and there we have 3 times 3 is 9. So we could see that the amount of the smallest in each of these is the square numbers going up. And in fact, the square of the size, as we called it. Like that's a size 3, and the square of 3 is 9. Now, what about the medium ones in a case where we have sizes in between the entire and the small? Like here on this 3 by 3, we said there's 9 minis, there's 1 massive, but how many 2 by 2s? Well, interestingly, the amount of 2 by 2s there is going to be the amount of 1 by 1s in the size a little lower. And we can kind of visualize that by here there's 4, but if we expanded these so that these squares grew to a 2 by 2, and now we're kind of looking at the centers of 2 by 2s with these 4 little crossing points being the center of a 2 by 2, we can kind of imagine it expanding and seeing how, yeah, there's 4 2 by 2s there, like how there were 4 1 by 1s there. So the sizes are kind of going to expand upward while adding the next square number. And altogether, what we have is that for a square of size x, we're going to have the sum of the first x square numbers as the total amount of squares. So on this larger example, we're going to have how many littles? The 4th square number, 16. How many 2 by 2s? I'll write the size of them in here. How many 2 by 2s? We got 9. How many 3 by 3s? Pretend that's a square. We got 4. And how many 4 by 4s? We got 1. And if we add all of these up, that number, the sum of the first 4 squares, is also known as the 4th square pyramidal number. Because if you imagined like marbles or pool billiard balls, and you imagined making a square shape out of them, you can imagine stacking the next smaller square number on top of that. Like you could have a row of 5 by 5 marbles, and a 4 by 4 marble set would fit nicely on top of that. It works similarly if you try and stack triangular numbers, making what can be known as, some would call triangular pyramidal numbers, but they're also known as tetrahedral numbers, because that shape of a triangular pyramid can be known as a tetrahedron, and it's a magnificent shape. So here we can see that the fourth square pyramidal number, meaning the sum of the first four squares, which typically is observed and is named after being a three-dimensional thing, is really also present in this two-dimensional shape in a flattened way. We've flattened a square pyramid with our question, the question of how many total types of squares are there. So that's pretty cool, and we can see that in general, it's true if I make a square grid like this, and it has a side length of n squares on each side. It will be the sum of the first n squares, also known as the nth square pyramidal number, how many total squares are in it. So the next question was how many rectangles are in something like this. Now you can imagine that's a much trickier question. I'm going to erase my square answers from these. Here I'll leave the square answers and we'll just try and sneak the rectangles next to them as the other options that are possible. Because remember, a square is one of the rectangles we're going to need to include. A square is just the most perfect type of rectangle. So here we only have one rectangle option still, so our answer still ends up being one total and one of the one option. There's no other rectangles I could make to fit in there. But here I've added a new type of option. Not only do I have the two squares from before, I also could make a 1x2 rectangle. I could make those, in fact, in two ways. I could make ones that go there, around that 1x2, or around its neighbor. And I could also go the other direction and fit 1x2s there, sort of like dominoes. I could tile this with dominoes, either with two going that way or with two going that way, meaning I have a total of 4 of those. Now, it may be a little harder to visualize how these add to the answer of the formula for how many rectangles there are. So let's just tally these up all together by noting that there are 9 there total. So how about the 3x3? Here we have the options from before, the squares, but we also have a couple rectangular options. I have a 1x2, and I might as well draw the sides in here just to make it extra clear. I have a 1x3, and I have a 2x3. And this is shrunk, but imagine that is my 2x3. And the others, like a 2x2 or 3x3, were already covered here with our tally. So now let's count how many of these new options there are. Well, with the 1x3s, I can fit 3 that way or 3 that way. So I have 6 of those total if I count both directions they could go. How about the 2x3s? Well, I have 1, 2 possible that I could fit that way, and 1, 2 possible I could fit that way. So we have a total of 4 of those. And how about the 1x2s? We could fit 1 or 2 on that line, and so we could do that 3 types of line there, meaning 6 types of them could fit in going that orientation. And we could also fit 6 more of them going in that orientation, meaning there's 12 of those total, counting both orientations they could be in. So let's again just tally these up and see that here we have 18 plus 4 is 22, plus from before, so we go 23, 27, and 36. And all together, all of these, counting all of those, we have 36 there. Now, these are square numbers again, but they're even more important than typical square numbers. And there are 2 ways to observe what they are, because there's a magical pattern in algebra related to this type of number. Now, this number 36 can be written as 6 squared, which 6, we may note, is 1 plus 2 plus 3. So we could write 36 as 1 plus 2 plus 3 squared. And we could also, in this case, write our 9 as 1 plus 2 squared. And here we could write it as 1 squared. And so we can see one way of finding the amount of rectangles turns out to be adding up the first amount of numbers up to your side length number, meaning the nth triangular number for an n-sized one. Triangular numbers are a name for these because we could draw the dots in a triangular shape. And like I mentioned, if we stacked these triangular shapes, we would get a tetrahedral number or triangular pyramid. And with these numbers, the magic about certain triangular numbers, when we square them, if we square a triangular number, we also get the same result as taking those individual numbers, cubing them each, and adding them. Meaning that 1 plus 2 plus 3 all squared after the fact is the same as 1 cubed plus 2 cubed plus 3 cubed. Pardon the sloppiness. And in general, if I go to any integer and add all the numbers up through there, finding that triangular number and square that result, it's the same as if I individually cubed each of those numbers and added them. Here, it's also the same pattern. I could go 1 plus 2, then square it, or I could go 1 cubed plus 2 cubed. So although these are taking a triangular number and then squaring it, they're also commonly referred to as the sum of the cubes, because here also, again, it's just the first cube, nothing left to sum. And so there's two ways to describe the awesome pattern we've sort of flattened here. We've taken a triangular number and squared it to find how many rectangles, or we could visualize it as counting an amount of cubes and adding up the sum of the cubes up through some number, meaning both of those will hold true on this bigger one. I'm not going to draw the rectangular options, but the amount of rectangles that are in there can either be written as 1 plus 2 plus 3 plus 4, then square that all, or as 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. And it turns out that's exactly 100. Now, the number 100's actually overrated in a lot of contexts. Our base 10 society gives it too much credit. However, the coolest trait about the number 10 isn't that it's 2 times 5 or that we have 10 fingers. It's probably that 10 is the sum of the first 4 numbers. And so since 10's a triangular number, it gets its square, 100, getting these superpowers. So this is one thing I'll give the number 100 credit for, being the amount of rectangles in a 4x4 grid shape, and also being what we could call the fourth triangular number squared, or the sum of the first 4 cubes. And this is harder to visualize in a geometric way than the sum of squares, so it's often just called the sum of the cubes instead of something like a square pyramidal number. But there are a lot of cool ways to try and interpret this as a figurate number as well. Figurate numbers being a common name for these numbers that represent shapes, such as a triangular number or a square number. Not usually a name for the how many squares in a grid game we're playing right now, but a figurate number is a pretty awesome term for things like polygonal numbers, such as triangulars. Now, since we've now unlocked how many squares and rectangles are in grids like this, I'll leave you with a question that if I ever make a full episode that's a little more polished than this about extreme square and triangle counting, I'll go into this there. But for now, see if any of you can figure this out and answer it in the comments. Are there any formulas you can figure out for different types of rectangular grid? For example, if I had a 4x5 amount of squares, still a square grid, but a rectangular shape of them. Can you figure out formulas for how many squares or rectangles would be in a non-square shape of square grids? So leave any comments if you have any guesses about that before we maybe revisit it in the future. But we're not done yet because we haven't looked at the triangles. They have stories of their own as well that are pretty awesome. So once again, to look at how many triangles of different types are in this, we're going to look at some smaller examples. And since this could be considered one with 4 essentially on its side. We got 1, 2, 3, 4 as sort of the side length. We're calling that a 4-sized one. And let's look at some 1 through 3 sized ones. Now, when we ask how many triangles, we have to be a little clearer. We could just be asking how many mini triangles, or we could be including larger ones, like here's a 2 by 2 triangle right there. And 2 by 2, remember, means a different thing than a square, so 2 by 2 might not be the right term, but a 2-sized triangle does fit in there a few times, as well as a 3-sized and a bunch of 1-sized. So we can kind of, again, break them into components of having a 1, a 2, and a 3 in that, having just these smaller sizes in what fits in each of them. But we also have to ask, do we count the upside down ones? Do I count ones that face down like that? And for our first game, we will. Because for the first thing that I need to show you is if we just count how many smalls there are, we get something very interesting. The amount of smalls that are just pointing upward, there is 1, there is 1 plus 2, there is 1 plus 2 plus 3. So the amount of small ones that are pointing upward is the nth triangular number for an n-sized triangle grid. But if we count the downward ones too, we add in a different triangle number. This one has the 0th triangular number sort of downward. That has the first triangular number of downward. And that has 1 plus 2 going downward, the second triangular number going downward. So the total we could see here is the third triangular number plus the second triangular number, the second plus the first. And if we looked at our bigger case of 4, while we're just counting tiny ones, we would get a similar thing where we have the fourth triangular number of upwards and the third triangular number of downwards. And that's all of the mini ones in there. But we also encounter another awesome pattern, which is that if you try and draw one triangular number, and in this case we had the third, and then we try and add the second triangular number over next to it, we'll draw it over like that. Well, we can kind of re-squash these shapes over in our brain into them being a square number. If you ever add a triangular number with the neighboring triangular number, you get a square number. And so it also turns out that if we want to know how many miniatures are in each of these, not only is it the sum of two triangular numbers, but even simpler, it's the square number again. The amount of totals up and down here, just counting minis, is the first square number, the second square number, the third square number, and here it would be the fourth square number, 16 minis in there. So interestingly, there's the square number amount of minis in a square grid or a triangular grid. The triangular grid is very different geometrically, but it still packs in square numbers. And with the triangular grid, we can really clearly visualize a pattern, which is that if I take the amount that's just in each row, but count up or down, like these three are in the same row, I have 1, 3, 5, 7, and it shows us that square numbers are the sum of the first odd numbers all in a row. Here we could also visualize that by like adding that, adding 3, adding 5, now I'm going to add 7. So we could also visualize it in a square way, but pretty cool that not only is it now seen as, oh yeah, I'm adding two triangular numbers in a row, but I'm also just making a square number. But I could also make that by adding up odd numbers, because the nth square number is always the sum of the first n odd numbers. So that's how many mini triangles are and stuff like that. But what about other sizes of triangle? Now, for a moment, I gotta wipe this off, and we're not gonna count downwards for this. The thing about downwards when we're counting multiple sizes of triangle is that the formula changes depending on if it's an even or odd side length. So you kind of need two formulas or one formula with a weird adjustable function that rounds things in the right way. And so that's a little trickier, and once again will be saved for a future episode, probably, if I ever go even more extreme with this square and triangle counting for you guys in a more polished way when I'm not recovering from sickness. But in the meantime, once again, feel free to leave a comment if you have any guesses or can figure out any formulas that could be applied for how many total triangles, if I was including downward ones too, would fit in these. Because here we only have the small size of downward, but what makes it weird is that in certain sizes, we also unlock a bigger size of downward ones. Like I can fit a 2-sized downward in there. So as you go up, if you try and do any investigations in how many total triangles of different sizes, including ones that are downward and any size in a grid like this, remember that you may need a formula that's different for even or odd side lengths. Now, to wrap up today though, we're just going to look up the cool pattern we can get if we find how many total triangles are there. Well, here we have one mini. Here we said we have the second square number minis and the third square number minis. Oh, no, wait, sorry. That was total amount. You got to bear with me because it's a one-take video. So we were talking about triangular ones here. Thank you for joining me on my more impromptu combo class lesson, by the way. I love you all. In any case, here when we're looking at just the uprights, we just had one triangular number worth. Like here there were 1 plus 2 uprights giving us 3, and here there was 1 plus 2 plus 3 uprights giving us 6. Now, looking at the bigger sizes, here I have one of the bigger sizes, and again here there's always going to be only one of the biggest size in one. But how many of the smaller sizes in between? Well, here I have a 2-sized one, and I can fit one there, and one there. And if you think about this being scaled up and these sort of becoming the centers of new other ones, as if this dot in the middle of each of these has expanded to be that square in the middle of each of these that is pointing downward, we can kind of see that it will be the same number of that size going up to that size there. And so what do we have here? We have the triangular numbers starting off and getting pushed up. And if the triangular numbers are what's starting off the pattern and continuing through the pattern, it's going to be the sum of the first n triangular numbers, which, as I mentioned, is the nth tetrahedral number. Because if you took triangle shapes of balls, like marbles or pool billiard balls, and you stacked them in a triangle shape, more like pool, you could make like a 4-1 with a 3-1 nestled right on top and a 2-1 and a 1, and it would look, the bigger you made it, the closer and closer to a almost sharp, perfect-sided pyramid, but with a triangular base and that amount of sides. So often called a tetrahedron, but a lot of people just call it a triangular pyramid or a triangular prism too. But these tetrahedral shapes, once again, are typically a 3D thing, and now we have found a way to flatten them with a question of how many upright triangles of different sizes are in a triangular grid. So the amount of total upright triangles in here, counting all the sizes, is going to be 1 plus 1 plus 2 plus 1 plus 2 plus 3 plus 1 plus 2 plus 3 plus 4. And it turns out that gives us exactly 20. Now remember, there are more we could add if we counted the downward. If we counted those, we'd be adding in 1, 2, 3, 4, 5, 6 small ones. We'd also be adding in a 2-sized one. So it gets a little trickier. It does relate still to triangular numbers, but they're iterated. Sometimes, in this case, the amount of new ones you get just every other size for some ways of looking at it. So feel free to try and leave your guesses or answers to what you think that total amount of triangles, counting the downward ones in different grids might be. But like I said, matters on if the side length is an even or odd number. Altogether, I hope you had some fun learning about how counting up shapes in a grid, like asking a silly-ish question like how many squares are in there, or how many rectangles are in there, how many triangles of different types are in there, can sometimes lead you to cool algebraic and geometric patterns. And sometimes those patterns go hand in hand, since there's a lot of fun ways to visualize what's going on with numbers and shapes, and sometimes it's kind of the same pattern that makes one number do a thing, or one type of number do a thing, and one type of shape do a thing. In any case, thank you for joining me here for a little wild one-take video lesson. I love you all. Have a wonderful day. I'll be back with some short videos when I'm fully recovered, but for now, might film some random shorter little rant lessons, sort of like this. Thanks for watching.